Okay, young people, we're going to talk about PES, Photoelectron Spectroscopy. It's not very hard, but it just proves more evidence. It just provides more evidence for the photoelectron effect and the shell model that we've used for a long time. So I'm going to get rid of my face so that there's plenty of room and you can see all of the slides. Okay, there's my face gone. And I also need to grab my pen. So let me grab my pen. Oops, that's not exactly what I wanted to do. There we go. Pointer options, pen, pointer options. I want some color other than red. Okay, so how does PES work? PES works on the same principle as what we call the photoelectron effect. And basically what Einstein predicted was that, or what he told us was true, was if we provide a photon of a specific energy, h nu, that's the energy that we can calculate that that photon has, then that will release an electron that has some sort of kinetic energy. But in order for that to happen, this photon has to be greater in energy than the ionization energy of the atom. Ionization energy being equal to the photon will only allow the electron to get just outside of the atom's reach, the neutrons or the nucleus's reach, and then it be pulled right back in. So we have to be really careful to make sure that we're doing that. And so we do that by making sure that we add the right energy photon. So here's the kinetic energy of the photon, and that is equal to a constant called h nu, h being Planck's constant times the frequency of the light that we have. So we can see that different colors of light in the electromagnetic spectrum can release different amounts of energy. So red light, green light, purple light, these all are identified by these things. But not all of these can eject electrons from certain atoms. If you see down here, it takes -2 electron volts or 2 electron volts to eject an electron. Well, the red light doesn't have enough. The green light does have enough and a little bit more, and the purple light has enough. But what about electrons that are not just on the outside? So PES does the same thing, the same principle. It has a source of photons, usually UV, or it could be X-ray, depending on the what we're trying to take away. Okay, and I'm not sure why it keeps doing that, but it does, and I'm not happy with it. Okay. So an X-ray. Okay. And depending on the energy, we'll release an electron from somewhere, and then those electrons travel through this detector, and the energy is analyzed and collected and then graphed. That's basically how that works, and we get a display out that tells us what's happening. So it's actually a pretty simple process when you think about it. It's just more complicated to explain. So we know a couple things about energy, okay? The things down here are lower in energy. These are low energy waves. These are high energy waves. That means blue and violet light is high visible energy light, and red is low visible energy light. And you're like, well, but infrared radiation can burn us. Yes, it can. I didn't say it didn't have any energy. I said it was lower. But UV, we can't even see them. If we stand out in the sun for too long, especially a pale baby like me or some of you, you get sunburn. So the photon has to have an energy larger than the ionization energy. That's what we were talking about. In order to release that electron, the electron has to have kinetic energy left over to be able to move. If it doesn't have kinetic energy left over and it's just sitting at the top, it will be drawn back in by the Coulombic force. So the photons typically used in the PES are either UV light or X-rays. And the ejection of an electron produces a positive ion. We already know that. If we take an electron away from the atom, remember it's minusing a minus, which produces an ion that is positive. Okay? So let's go here. Ultraviolet photoelectron spectroscopy is only energetic enough to release valence electrons. It is really not energetic enough to release anything else. So we can calculate the kinetic energy of our photon, of our electron, by knowing the energy of the photon and subtracting the ionization energy that we need to achieve. And that will give me the energy of the electron. just like the ionization energy we can get from the photon minus the kinetic energy of the electron. So this is what we know. We also know that ejecting a valence electron takes less energy. This takes less energy than a core electron. That means one closer to the nucleus. Valence is on the outside, core or inner on the inside. So we understand that to be true. So X-rays are used when we're trying to eject a core. When we're trying to eject a core, sorry about that, it's my reminder to go home. Okay, so when we're trying to eject an electron from the core, we need more energy. So X-rays, a higher energy ray, is going to be used because remember, these electrons have to have enough kinetic energy to escape the atom. In order to do that, they have to have a photon with high enough energy to be more than the ionization energy. And since it takes more energy to release a core electron, then we have to have a higher energy ray, which is why we use an X-ray for those situations. So here we are. We understand that excess energy must be carried off by the electron. If we have a photon that is greater in energy than the ionization energy, then the electron is going to have kinetic energy. That means that the atom had to absorb an equal amount of energy to the ionization energy in order to release that electron. There's a cost. There's an energy cost. So the atom has to absorb that from the photon. And anything left over is the energy of the electron, the kinetic energy of the electron. So we know that in order to get this to happen, we have to have an understanding that the H nu is equal to the ionization energy plus the kinetic energy of the electron. This is the energy absorbed by the atom, right? And this is the energy of the electron escaping. Okay? So we're going to see an equation that's a little different because it's describing the ionization energy. Remember, when you see the word binding, it's also the same thing as ionization energy. It is the same thing, and you might see it, so I'm warning you. Binding energy and ionization energy are one and the same. So if I look at this equation and compare it to this one down here, it makes perfect sense. It's the exact same equation, I just put H nu on the other side. And so this is the same exact equation that we talked about. Radiation has to be absorbed by the atom to release the electron. That's the ionization energy. The excess energy is the energy of the electron escaping, moving away. And the photon had to be equal to that energy. Okay, so now I'm going to have stuff in the way of my good stuff. Hang on, let me erase some stuff. Because I'm going to have stuff in the way. Yep. Okay, so absorbed energy from the photon, that's the ionization energy, and the energy of the ejected photon. So this is the energy absorbed by the atom. That's what ionization energy is. It's the energy required by the atom to release that electron. You have to give that energy. It's the cost. And so if you don't give that energy, you don't release an electron. That's the kind of idea that we've got going on here. Okay, so the values of ionization energy found reveal information about the elements present in the orbitals from which they were ejected from. So now we can start seeing not only the energy levels, but the orbitals themselves. We know that lower ionization energies are for valence electrons, so things that are on the outer side. And higher ionization energies are for core electrons, things that are closer to the nucleus. So the closer you get to the nucleus, the more tightly held it's going to be, the more energy cost you're going to have to pay to get that electron from there. So we know that these higher ionization energy electrons are coming from core electrons on the inside. Okay, so you're going to see data in a couple of ways. So I want to make sure that you understand this. You don't see any peaks on this graph, but I want you to see the axes. We're going to have number of electrons going up the y-axis, and on the x-axis is going to say binding energy or ionization energy. It may be in units of millijoules megajoules per mole or electron volts. Okay? Electron volts, because remember, electrons moving produce energy or produce electricity. So, this is the problem though. Some spectra can be plotted with 0 here and increasing energy. Okay? But some can be plotted with energy increasing going this way, where you have 0 over here and we have greater values over here. So you need to really make sure, no matter what the unit is down here, that you've read the scale on the x-axis. Is it going from right to left, from 0 to higher, or is it going the other way, from higher to lower? And so this is going to be something that you have to really pay attention to in order to make sure that you're getting things right. And I've seen it both ways. So I've seen it in questions both ways. So I just want you to be prepared for that. Okay? So the peak height that we see is directly proportional to the number of electrons ejected at that energy. So what are we saying? If we see two peaks with different heights, so we see this height peak right here, and we see this height peak right here. Well, we see that this peak is about half the size of this one. So that means there are 2 times the number of electrons at this peak than this peak. So if this peak represented 1 electron, this would be 2 electrons. If this peak represented 2 electrons, then this one would be 4 electrons, so on and so forth. You get the idea? So we're going to be looking at the size of the peak. The taller the peak contains more electrons. And sometimes we don't see a scale on the y-axis, so it's going to be a little bit more difficult to see those things. So if we look at this very carefully here, we start seeing some things. Here is a hydrogen atom. We see hydrogen has one peak on the PES scan at 1.31 megajoules per mole. Okay, that basically is equivalent to 1,312 kilojoules per mole, which we know is the ionization energy. That's the energy, minimum energy to require it to remove an electron. Remember, to keep it moving, though, it's got to have more energy. So you will notice this is a little tiny peak. It only has one peak. Okay? We can't tell if it's a peak that has more than one, but we just know it's a single peak. So we assume that this is the 1s2 energy level. And since it's the only energy level, it takes 1,312 joules to remove it. Okay? So this is the amount of energy required to eject electrons from 1 mole of hydrogen atoms, and that's what it's talking about. So if you look at this one, this is helium. Notice something happens. Well, what's happening here first? First of all, helium just increased its nuclear charge by 1. It's got now a nuclear charge of 2, which means it's pulling on those electrons even greater. That means it takes more energy to remove those electrons. So you're going to see everything shift toward greater energy as we go across periods. And then once we bounce down to the next energy level, we'll see significant jumps, and then we'll start over that process again. So we see one peak, but notice this peak right here for helium is about double the size of the one for hydrogen. So we're going to say that this peak represents the 1s2 electrons. There are 2 electrons in that peak, not just 1 electron. Okay? How are we doing so far? Hopefully well. So both hydrogen and helium have electrons in the n equals 1. That means energy level 1. But because we have a greater effective nuclear charge on helium, that's why these electrons are a little bit more energy cost to get away. So let's see what happens to lithium. Okay, lithium, we see something happening. Now we have 2 peaks. So lithium has 2 peaks. Why? Because we have 2 energy levels. We're now in energy level 1 and energy level 2. We see the peaks. This one is half the size of this one, which means this has double the number of electrons. This one is higher in energy than this one, which means these are closer to the nucleus, being held more tightly. So if we know anything about lithium and we know anything about these things, these have to be core because they're higher in energy, and these must be the valence electrons. Okay? So if we look at that from that perspective, this is going to be the 1s2 electrons, and this is going to be the 2s1 electrons. And we can see that very clearly. Okay, then we get to beryllium. Notice what happens. Beryllium went up, its Z effective increased by 1. Its Z effective is 2, where the Z effective of lithium is only 1. So we pull electrons more tightly. So it's going to take more energy. Notice these two peaks. This peak and this peak are the same size, meaning they have equal numbers of electrons. This one has more energy than this one, requires a lot more energy. So this must be core, and these must be valence. So I'm going to say these are the 1s2, and these are the 2s1. Now, if the scale was flipped, in other words, if it were not increasing going right, see the arrow saying increasing energy this way? If it were increasing the opposite way, then the PES peaks would be flipped. They would be flipped. Okay? So you'd see the 2s1 first and then the 1s2 later. So just be really careful. Be really careful how you read that x-axis. It's going to be super important how you read that. Okay, finally, we see boron. And notice, we see this tall peak that's the same size as this peak, still the same size. And then all of a sudden we see a peak that's half the size of both of those. And you see this energy is extreme, and this energy is a little bit more, and this energy is a little bit less. So these over here are core electrons. All of these electrons over here, all of these are valence electrons. And we notice that the S's are going to be held a little more tightly than the P's. So this is 1s2 electrons, this is 2s2 electrons, and this is the 2p1 electron. So if we're looking at it from that perspective, we can see that it starts making sense, and the shell model is really put forth here. So PS determines the energy needed to eject electrons, which is called the ionization energy, also known as the binding energy. You need at least the ionization energy to get an electron. But if you really want the electron to escape, you have to add more than the ionization energy. This PES data reinforces the idea of the shell model, the SPD and F model of the atom. And it really gets down to the whole idea that there's an electronic structure here beyond what we thought in the first place. Okay, so we know that there are different subshells in different energy levels. So we clearly saw from the peaks that we saw that we could see the S and the P sublevel when we got to boron. We could see the difference there. And we know that there's a difference, that the S's take a little more energy to get electrons away than the P's do. So they're a little bit more shielded than the P's are, even if we go further into that. Okay? Peaks in n equals 1 and n equals 2 are similar in size. So when we talk about the S electrons, we saw that those peaks were the same because they all had 2 electrons. But there's a difference in ionization energy because of the Z effective. Remember the nuclear charge. The effective nuclear charge makes a difference. The higher it goes, the closer it pulls, which means those electrons are going to be harder to take away. Okay? It takes more energy to remove an electron from n equals 2 and 3 than, it takes more energy to remove electrons from n equals 1 than it does from n equals 2 or 3. Because these are closer to the nucleus. Closer to the nucleus means there's more nuclear charge pulling on them. And finally, within any subshell, it takes the most energy to remove an electron from the S subshell, or the core. I want you to kind of remember it as the core. S's will take more than P's and D's and F's, but I want you to remember core electrons take more energy. Okay? So it's our expectation that it takes more energy to remove an electron from n equals 2 than n equals 3, and even more from n equals 1. Okay? So, do all electrons in a given shell have the same energy? And the answer to that question is no. Electrons in a specific sublevel, S, P, D, or F, have similar energies. That's why we have peaks that look like this, because there's area underneath here that's kind of averaging out the energies of all of those peaks within that range. And so they have similar energies, which is why they're being captured here, but not exactly the same. Okay? So we're going to stop right there, and I'm going to do another video for the next one.